All right, let's talk about an engineering project that sounds like it's straight out of science fiction, but is actually getting very, very real. Building a giant electromagnetic cannon on the moon.
To get why we'd even think about doing that, you really have to start with this number. It costs about $1.5 million to land a single ton of cargo on the moon. I mean, talk about an expensive delivery fee.
But here's the real kicker, the thing that's holding us back from building anything meaningful in space, getting back up. Just think about it for a second. Every drop of fuel you need to leave the moon is fuel you had to pay all that money to land there in the first place. It's this terrible, expensive cycle that engineers call the gravity well.
So how do we get out of this trap, right? How do we break free from what some people call the tyranny of rockets and really truly open up the solar system for business?
Well, the good news is the moon's gravity well is way, way shallower than Earth's. You only have to get up to 2.4 kilometers per second to escape its pull, versus a mind-boggling 11.2 here at home. That's a huge advantage. But to really use it, we need a smarter way to get off the surface, a way that doesn't involve fuel.
So let's get to the solution. It's a concept that's actually been around since the 1970s, but it's only now, with modern tech, that it's becoming something we can actually build.
It's called a mass driver. You can also think of it as an electromagnetic catapult. The idea itself is actually pretty simple, but incredibly powerful. It's basically a giant, high-tech slingshot that uses electricity and super powerful magnets instead of rocket fuel.
Now, what's really cool about this schematic is that it shows you the secret sauce. It's modular. This isn't one giant machine we have to somehow land in one piece. We can build it section by section, with each part delivered by something like SpaceX's Starship.
So the key thing to get here is that the whole system is electric. Once you have a power source on the moon, like a big solar farm or a small reactor, you essentially have unlimited launches. The fuel is just sunlight, and guess what? That's free.
So we know what this thing is, but the big question for engineers isn't really if we should build one. It's what should the first one actually look like.
And this is the central debate. It really boils down to a classic engineering trade-off. Do you build for raw, brutal acceleration, or do you build for massive, sprawling infrastructure? And this table lays out the two options perfectly. On one hand, you could build a really long, gentle track, we're talking kilometers long, that accelerates things at a pretty comfy 3 Gs. Or you could build a short, incredibly powerful cannon that hits its cargo with hundreds or maybe even thousands of Gs.
For our first steps, the consensus is pretty clear. Go with the cannon. The goal isn't to launch people or delicate science experiments, not yet. It's about launching bulk resources, specifically water ice from the lunar poles that we can turn into rocket fuel up in orbit.
So how does anything survive those insane forces? Well, you basically have to treat the payload like an artillery shell. All the electronics are potted in solid resin so they don't shake apart, and the whole thing sits inside a protective carrier that guides it down the barrel. But of course, there's a catch. When you fire a 1-ton payload with that much force, you get an equally massive kickback. Newton's third law is still the law even on the moon. We're talking a recoil of 9.8 million newtons. To give you some perspective, that's like having 2.5 Boeing 747s at full throttle trying to shove the entire cannon backward. To handle a kick like that, the whole launcher has to be anchored deep into the lunar bedrock with these massive pylons. You're basically turning part of the moon itself into one giant, stable, firing platform.
So, how would we actually build this thing? Well, let's look at the plan. It's a step-by-step process that feels surprisingly down to earth.
It all starts with robots. They land, set up the power, and literally pave a road out of molten moon dust. Then comes the foundation, the pylons, followed by the high-tech engine itself, the superconducting magnets. Every single delivery from Earth builds on the last one.
And this right here, this is the paradigm shift. This is the real game changer. Because once that factory is up and running, you completely flip space economics on its head. You stop shipping bulky satellites from the bottom of Earth's deep gravity well. Instead, the moon provides the metal, the structure, all the heavy stuff. All you need to ship from Earth are the brains, the lightweight, high-value microchips. It's like building a car factory on another world and only having to ship the engine computers.
And look, this isn't some pie-in-the-sky sci-fi dream. This roadmap aligns almost perfectly with the current timeline for NASA's Artemis program. This is a natural, evolutionary next step for our return to the moon.
Okay, so let's zoom out for the final piece of this puzzle and see how this one project builds into something that is truly transformative for our future in space.
This cannon is so much more than just a lunar launch pad. It is the first exit ramp onto an interplanetary highway. The moon becomes a cosmic gas station, making it possible to have these ambitious missions to Mars, to the asteroid belt, and even beyond, all without lugging fuel up from Earth.
On an even grander scale, this kind of tech lets us start thinking about our energy future as a species. There's this concept called the Kardashev scale, which measures how advanced the civilization is by how much energy it can use. Well, by using this mass driver to launch thousands of solar collectors, we could actually start building what's called a Dyson swarm, a massive network of satellites that would capture a huge chunk of the sun's total energy. That's a major step towards securing our future out there in the cosmos.
And this really is the most important takeaway. We stop thinking about space as a place we just visit. We start treating it as a place where we build. This isn't about planting a flag anymore. It's about laying the foundation for a permanent, interconnected, and self-sustaining presence across the whole solar system.
So that's a thought I really want to leave you with. What kind of new economies, what incredible discoveries, what unimaginable futures become possible when the cost of moving stuff through space drops to almost zero? What happens when space finally has shipping lanes,